We have already heard from Dr. Unnikrishnan, but of course, he is a professor at the Tata Institute of Fundamental Research. And he's, of course, published widely in quantum mechanics and works on the Indian LIGO project. And he's been a super valuable member of the discussion all weekend long. So let's give him our full attention as he tells us about the gravity of the universe and the physics of dynamics and relativity.
Let us see in the dark.
We know that this universe contains a lot of matter, energy, and therefore it has a lot of gravity. And today I'm going to talk about the gravity of the current universe, that is as we see today, and its relation to the laboratory physics of dynamics and relativity. Now I'm going to say that the gravity of the universe is the true basis of all dynamics and motional relativity. This I call a theory of cosmic relativity. Now, if you look at the fundamental theories of physics, dynamics and relativity, Einstein's theories of relativity 1905 to 1915, quantum mechanics and quantum field theory, by 1930, these theories were completed. Then theories of matter and their interactions, what we call a standard model of particle physics, started around 1900. It's still continuing to be developed. But modern cosmology came only after 1930. After the fundamental theories of relativity and quantum mechanics were already completed. So we didn't know anything about the gravity of the universe or the universe itself by the time these theories were considered completed. What is the universe we knew before 1925, say? It was an elementary universe, Milky Way, certain nebulae, a small universe. This is our nearby universe. After Hubble's observations in 1929, we realized that the universe is at least 1,000 times larger with matter everywhere. When you say a universe is 1,000 times larger, we mean the matter energy content of that universe is 1,000,000,000 times larger. Volume, cube of the size. So we had a small universe before 1930. Then we have this vast universe in today's knowledge. So this our universe as we knew it, when these fundamental theories were completed, is something negligible, gravitationally, matter, energy-wise, and so on. Today's universe, we know roughly the matter content, what kind of gravity should be generated by this matter. When I say gravity, I mean the total gravitational potentials which interacts with matter, or what we call in quantum mechanics, when you write a Hamiltonian, what should be the term we should put for the gravitational energy of a particle. The difference is enormous because the gravity is 1,000,000,000 times larger than what we thought it was. So the successful and accurate theories that we use today were formulated when they were formulated. This gravity was not known, which is a very, very significant factor. Then the question arises, are these then the final theories of dynamics and relativity? Because gravity affects every physical process. How do we decide? All what I'm going to talk about today is contained in this book, which was published 3 years ago. It's called New Relativity in the Gravitational Universe, published by Springer. Now, a way of making a decision, as told by Einstein, he wrote it in 1912 when he wrote a paper on superconductivity. The theoretical scientific researcher is not to be envied because nature, or more precisely put, experiment, is a merciless and not very kindly judge of his efforts. She never says yes to a theory. In the best case, merely perhaps. But in most cases, simply no. If an experiment agrees with the theory, it means perhaps. If it does not agree, then it means no. Every theory is sure to experience its no someday. Most theories already do so soon after their formulation. Of course, he may not have expected his own theory might face the situation, but that's a different matter. Now, my point is that the gravitational universe, as we know today, from observations, is an absolute frame with an absolute time and a unique reference frame for the motion of everything in this universe relative to the average matter frame of the universe. So there is one definite falsifiable prediction just from the fact that we have an absolute frame, that the relative velocity of light is Galilean, c plus or minus v, just like the relative velocity of other Galilean waves like sound. So that is one falsifiable definite prediction which can be used to distinguish between theories. Now, if you look at the gravitational potentials generated by matter, for example, in this room, from the Earth, gm by r, we can calculate it, and there is a number which comes out, and we can normalize it with the quantity square of the velocity of light, which has the same units. We get a number of about 10 to the 8 meter square per second square. Now, the gravitational potential generated by the sun in this room is 10 times larger. It's not smaller. The force is smaller, but the gravitational potential which matters for the Hamiltonians we write is 10 times larger. And if you take the galaxy, it is 1,000 times larger. So we know the pattern is that distant masses dominate when we consider gravitational potential at every point in this universe, including this room. Therefore, we can calculate, at least approximately, knowing the average density of matter and energy in the universe and integrated up to Hubble radius. This have been mentioned many, many times in this meeting. And we get another number, which is this 10 to the 17 meters square per second square, which happens to be very close to the square of the velocity of light. This is a known fact. It is known from early days of cosmology. So, based on this fact, I'm saying all motional relativistic effects and the laws of dynamics are the gravitational effects of matter and energy in our universe. And that is a theory of cosmic relativity. And by this, I'm implying that things like special relativity is an entirely wrong theory, should be replaced completely, totally. And then now I want to give proofs, including laboratory experiments for this fact. If you look at a Galilean wave like sound, coming out of a source, you can measure its velocity, relative velocity, by measuring the distance travel in a particular amount of time. Now, if the source is moving while emitting that Galilean wave, the velocity of the waves through the medium does not depend on the velocity of the source. Whether it is sound or light or any other wave, none of the waves, their relative velocity depend on the velocity of the source. The only question is whether the relative velocity depends on the velocity of the observing frame. So velocity of sound, we know it does depend on the velocity of the receiver, in a Galilean way, c plus or minus v in one-dimensional case. Now, if you look at the history of light, we had this notion of an absolute ether in the 19th century. Everything happened in that absolute frame of the ether. But in 1905, Einstein had a different idea where ether hypothesis was not needed. And there so if light is propagating in ether as a medium, of course, the relative velocity is Galilean, just like velocity of sound. However, in Einstein's hypothesis, called the light hypothesis, the relative velocity of light was independent of not only the source, also of the observer. It was an invariant constant of nature. So the unconditional invariance of the relative velocity of light in free space is a defining postulate of Einstein's special theory of relativity. The other postulate, the principle of relativity, is common to either the Lorentz-Poincare theory or any other theory of relativity. The principle of relativity is a common postulate, but the defining postulate of Einstein's theory is the constancy of the relative velocity of light, which says that the relative velocity of light is the same whether one is chasing a pulse of light or whether one is moving towards a source. Now, Einstein's theory, special theory, is the basis of all other theories of physics today. That's the basis. Even for general relativity, that's the basis. You say you move far away from massive sources, the physics of special relativity applies. Now, what is the evidence? Experimental evidence that the relative velocity of light is a constant. In the last 100 years, there is no experiment which has verified this. There is a misconception that Michelson-Morley experiment is a proof of the invariance of the relative velocity of light. So let me look at it briefly. Michelson-Morley experiment involves two arms of an interferometer, and being an interferometer, the light propagates in both directions. It goes to a mirror, gets reflected back, and returns. So it's a two-way propagation experiment. Now, if there is a stationary interferometer going back and forth, we expect same velocity. However, in a moving frame, and if it is in either kind of a medium or an absolute frame, then you would say the velocity in one direction would be c minus v, and the velocity in the opposite direction is c plus v. This was a logic used by Michelson. Therefore, the total time taken in each arm is L distance divided by c minus v plus distance divided by c plus v, the return. So therefore, you see the total time taken is 2L by c. Then there is a small second order correction, 1 minus v square by c square, which is what Michelson was hoping to measure in his experiment. And when the experiment was done over years, nothing was seen. That second order correction in the brackets 1 minus v square by c square was not seen. The total time measured was equivalent to 2L by c in a two-way propagation. Therefore, the principle of relativity was verified, that you cannot measure your uniform motion, you cannot detect it by an experiment in optics. That was the conclusion. And this was explained by Fitzgerald and Lorentz, saying that it is not Galilean transformations which fits in this two-way situation. It is what is called the Lorentz transformation. But in the Lorentz-Poincare theory, it is important to understand that the propagation of light is still Galilean because there is ether. So there is ether with the Galilean propagation, there is length contraction, there is time dilation. These three phenomena together mask the fact that light might be going in a Galilean way. However, in Einstein's theory, situation is completely different. It's postulated that the velocity, relative velocity of light is a constant. Therefore, you don't need to invoke time dilation and length contraction in the frame in which the experiment is done. However, there is not a single experiment to date that verifies and proves Einstein's light hypothesis that its velocity is an invariant constant in one-way propagation. Believe me, there is not a single experiment. You can check it. But we thought and we were taught that this is amply verified in many, many experiments. That is not true. In fact, it can be shown briefly Let me try to explain it, though some people may know it. As I said, there is a second order correction which comes, which is what Michelson was trying to measure. But suppose time runs slower while in movement. That t prime is t multiplied by square root of 1 minus v square by c square. Then one of those factors in the 1 minus v square by c square root 1 minus v square by c square cancels out. Therefore, the t prime now becomes this if there is a time dilation phenomena. And if there's a length contraction phenomena, there is one more square root of 1 minus v square. So together, you get 2L by c. You see, even if you assume that the relative velocity of light is Galilean, if there is an absolute frame, whatever that absolute frame is, if these are real physical effects, then the whole thing together gives you 2L by c. So the summary is that no two-way experiments is capable of deciding whether the propagation of light is Galilean or Einsteinian. Michelson-Morley kind of experiment is consistent with both hypotheses. Okay, that's my statement. So we need to measure the relative velocity of light in true one-way propagation. How do we do that? How do we do this kind of a measurement? We know that there is no empirical proof to decide on these two till now. Nobody has managed to really measure the one-way relative velocity of light. The problem is this: if when you want to measure the relative velocity of light or relative velocity of anything, you need a starting point, you need a final point. You make the system propagate from the starting point to the final point. And you fix the distance, and then if you can measure the time difference between these 2 points, you can measure the velocity. So velocity is a hybrid derived quantity. It is not a directly measured quantity here. So just a distance divided by the time interval. Now in a moving frame, the same experiment you can do in a moving frame. And again, you have to measure the time interval taken between the starting point and the final point. Same distance is not changed. The problem is you have to synchronize these two clocks. It is not difficult to synchronize two clocks if you are trying to measure the velocity of somebody running on a track. But if you want to measure the velocity of light, which moves very fast, synchronizing two clocks, two separated clocks, is a big conceptual issue. This has been amply discussed by Poincaré in his writings, how to synchronize the clocks, and he concluded that it's a convention, actually, synchronization of clocks. So, a pulse of light going from one point to another, one clock to another, and your task is to measure that in a moving frame. The need for synchronizing this clock, the principle of relativity does not allow one to know whether we are moving or not. So we don't know whether we are moving. For example, this room is moving at a enormous velocity, but we cannot know it. So therefore, we cannot assume anything about our motion to synchronize the clock. There are two ways to synchronize two clocks. One is to send a pulse of light from one point to another. But that's what we are trying to measure. So that would not. Another way is to synchronize two clocks and move that clock slowly to the other point. But then you need a theory of moving clocks, whether time is changing or not, we don't know. So all this is a problem. So it turns out there is no way to synchronize two clocks. So you need to find a method of measuring one-way speed of light by sending a pulse and relative to a frame which is moving inertially. And you also need to eliminate the need for two clocks. How do you do that? Now, for that, you notice that if you have two pulses, one going straight and another going in a curved path, the actual distance moved by this pulse does not depend on the shape of the path. The shape of the one-way path here, for example, in the second one, there are two pulses which are moving. Both pulses travel exactly the same time, the same distance in a interval delta t. Therefore, since it's independent of the shape of the path, we can do this. We can do this. And automatically the distance traveled by these two pulses are the same. But now I bring it back to the same clock and I don't need two clocks. So one can eliminate the need for synchronizing two clocks if you have a loop path. But if the loop path is such that there's a straight stretch, then you can also have completely inertial motion. That's the difference between SANAC kind of configuration. So the point is that instead of doing this kind of an experiment which needs separated clocks, you can do an experiment of this sort and you can measure the one-way speed of light related to a inertially moving frame. Okay, but this idea has to be validated. Of course, if you measure this, if you get a slope proportional to velocity, is Galilean. If it is independent like this, then it's an invariant constant. Now I'll just immediately present the experimental proof. But before that, people who do not want to look at the details of actual experiments, I want to present a remarkable proof which everybody can test out, check for themselves. And it's a very simple proof which proves that in a world where there are Galilean waves like sound, Einstein's light hypothesis is inconsistent. I'm going to prove in the next 5 minutes that special relativity is internally inconsistent. How do you do that? I have a system where I can have a starting point, initial instant, where I can simultaneously send a pulse of sound or pulse of any Galilean wave and a pulse of light emitted by a moving observer. So it's a simultaneous event. Two pulses are emitted simultaneously. So it's a simultaneous means for everybody it's simultaneous event. Delta t, delta x is 0. Now it goes around this loop path. And by the time the pulse of sound comes back once, the pulse of light will go around 1,000,000 times because the velocity is about 1,000,000 times larger. Each time the pulse of light goes, the moving observer counts 1, 2, 3, the point of crossing, which is a simultaneity event. So finally, we make the experiment such that the moving observer detects both the pulses simultaneously. So the sound has moved once in the loop, light has moved, let's say, n times, where n is the order of 1,000,000. And the experiment is stopped. So there are two simultaneous events. Two pulses are emitted simultaneously, two pulses are detected simultaneously. That n is an invariant, it's an integer. Whether the moving observer counts or an observer outside, stationary observer counts, it's the same n. It has to be. Though their clocks are different, the count is an invariant, relativistic invariant. Let us see whether this is true, given Einstein's light hypothesis. The lab observer can calculate. I don't want to go into great detail of this. Lab observer can calculate by the time the light goes around, and then there's an additional distance the observer has traveled, v times t. So n times L by c, light goes around so many times, plus the extra distance the observer has moved because he has a velocity. So the total time taken has this equation, simple equation, from which you can, and whereas a sound, where I indicated the velocity of sound as s, that goes around once. So n is equal to 1 for sound. So we have the second equation. From these two equations, we can reduce n. Anybody can calculate this. We get C minus V divided by S minus V. Now, that is observation by a stationary observer from outside. The moving observer, he can also calculate. His time is different, delta t. His distances is in a different frame. So you can calculate this. The distance you can verify that the distances in his frame obey that equation. And finally, when he calculates n, he gets C divided by S minus V, which is not same as the n calculated by the other observer. You see, the only way this can be consistent if the velocity is C minus V for both observers. So this very simple system, this very simple thought experiment tells you that Einstein's light hypothesis is inconsistent when we consider paths more general than straight paths. Okay. However, some people may not be satisfied with this kind of a logical proof, even though it is impeccable. So let me give you a real experiment. So I said earlier that I have a system where I make the wave goes around in a loop path so that I avoid the need for a synchronized clock, two clocks. And the clock itself is moving inertially. I reconstruct that experiment first for Galilean wave because I need to validate my technique. If I use a Galilean wave in the experiment, I should get back the Galilean velocity, relative one-way velocity. So I have some experiment. The details can be read in my publication, the reference I will give you. Anyway, finally the result is that I verify that sound is a Galilean wave. That is not surprising. That is what we wanted. Now I can do the same experiment in the same configuration using light. Then it becomes just a comparison between sound and light. And that needs an interferometric experiment, more sophisticated experiment. It's a difficult experiment, but the result you can see. The relative velocity, that the time taken by light to go and come back into the same moving observer increases with the velocity of the observer. Both results are identical. Of course, the slopes are different because they have different velocities. So this is a reference where some details can be read. It's an open access paper. The point is that this is sound, this is light. Both have the exactly same behavior, which shows that light one-way velocity is Galilean. This is the first time somebody has verified the true one-way relative velocity of light by a real experiment. And I already told you a thought experiment where the same results are obtained. So the point is, I have direct laboratory experimental evidence that Einstein's light hypothesis is incorrect. And since that's a defining postulate of Einstein's theory, by his own criteria of how experiments decide theories, his theory is a no. It's a resounding no. Okay. Now, why does this happen? Now, if you look at, I want to give some more evidence for this. If you look at clocks in Einstein's relativity, he wrote in 1905, if there are two clocks synchronized and one of them moves and comes back to the same point, it will be slower by particular amount. Like that, it goes and comes back, then you can compare. The time is different for the two clocks. One is t, other is 1 minus v square by 2c square in the approximation. Now, let's look at a real experiment, whether this is true. This is a prediction of special relativity. Clock, which is moved and comes back to the same point, it should have time dilation. Measured in various experiments, but let's look at a very specific kind of experiment. Have the two clocks synchronized, let's say near Bombay. Then I move one of the clocks to some velocity, some distance. And of course, in this situation, I cannot compare these two clocks because they are separated already. However, theoretically, I will assert that the clock which is moved should have a time dilation. It should be running slower, though I cannot exactly verify this. And that how much this is going to be the difference if there is a velocity. I can move it further. Because Earth is a globe, so it can come back. Then I can do a comparison, right? So each time I move some distance at some velocity, there is some time dilation. I just integrate or sum up all those time dilations. Each movement is a time dilation. So there is an integrated time dilation. I should have some time dilation, whatever it is. However, this is not what you see in the experiment. What you see in the experiment is the clock which is in the laboratory, which never moved, that has a time dilation relative to the clock which has been moved. Exactly opposite result. This is a result you see in a real experiment. And the experiment was done in 1971, though the result was presented in a different way, so that this crucial fact is masked in the publication. But this is what happened. So here, Einstein's theory is explicitly violated, and the reason I will we are immediately coming to the reason for that. But this prediction is violated very straightforward way. Now we look at GPS, which everybody uses. We know how it works. There are satellites at different places. You can use Einstein's theory to say that the time difference between the receiver and the emitter in the satellite, T1, T2, T3, and so on, that's all what is recorded in a GPS receiver, this time difference. That is converted to a distance using Einstein's theory. Since velocity of light, relative velocity of light is independent of the source as well as the receiver velocity, one should be able to use this as a formula to be used. But this is not the formula which is really used. Einstein's theory of special relativity in GPS, if it was used, this should have been the formula which is used to convert the time intervals into spatial intervals. But what is used is a different formula which looks more complicated. Let's not go into details of that. I have explained in great detail in my book what it means. But essentially, that formula is equivalent to assuming that relative velocity is c minus v, where v is the velocity of the receiver. You can see it is a very simple algebraic exercise to verify that that is what is used. That is how your formula comes about. Okay, so that is another very clear example in today's situation, which everybody can verify. This light mobile phone which I carry is a heavy burden of a wrong theory. Okay. So I have completed all the experimental proof I wanted to give, because now I want to briefly say what is really happening. All evidence confirms the existence of an absolute determining frame for dynamics and relativity. And I know it is more general than electrodynamics, so it is not old either. And I have argued that this absolute frame is the gravitational frame of the entire matter energy in the universe. Because of the large gravitational potential. Now, the point is that people have tried to implement the Max principle by calculating the gravitational potential, deriving inertia and so on, like Dennis Yama, Alfred Kassler, Schrodinger. Various people have tried. All of them failed. Einstein himself failed. But now we understand why none of the initiatives to implement Max principle succeeded. A Machian framework necessarily has an absolute frame. Therefore, it implies a rejection of special relativity totally. You cannot implement Max principle and also try to preserve special relativity. But all the previous attempts tried that, and that's why it failed. Mach's principle can be implemented only by totally rejecting Einstein's special relativity. And that is what, so therefore, as I mentioned yesterday, the Einstein's equation should have had a permanent term of the energy moment tensor of the universe itself permanently in the equation. You cannot remove it. This is a local Tik, you can put zero. Then you get what is called vacuum Einstein's equation. But vacuum Einstein's equation is a non-existent myth. We are in this universe where there is the matter and energy of the universe is always there. You cannot remove it. You cannot go anywhere in the universe where this Tik is zero. So this is a full Einstein's equation. But as soon as you write this has absolute frame. It is not obeying general coordinate invariance. So special relativity is wrong, entirely wrong. General relativity is incomplete as it is. You have to just add this term which makes it an absolute frame theory. The clock then is moving in the universe where there is a lot of matter and energy. There's a gravitational potential. Now, if you look at the frame of a stationary clock, it sees one gravitational potential. If you are in the frame of a moving clock, what's the gravitational potential? It will be modified. That is, a moving frame has a different gravitational potential in this universe than a stationary frame. It is that difference in the gravitational potential which generates the time dilation between these two clocks. And that time dilation is absolute. It depends on the absolute velocity of the clock in the universe. Yeah. So there is only one frame in this universe where things are homogeneous and isotropic, which is there is a true stationary frame possible in this universe. We can use either the microwave background to decide what that frame is, because we cannot see the galaxies moving and so on. And in all other frames, if we move, there's a current of matter and energy in the universe in our frame, which generates a vector potential kind of a thing, which is what people like Syama had done. And I want to show you mathematically what happens. If you are in a truly stationary frame, and if you try to write a metric mathematically in that frame, it will look almost like the Minkowski metric. Now I am going to do a Galilean transformation, not a Lorentz transformation. I'm going to do a Galilean transformation on this metric. And I get this written in the matrix form. I'm writing only two coordinates, one's time and one space for clarity. This is what I get. Galilean. It's a Galilean transformation. But from this Galilean transformation, you can see I get the time dilation factors here. And I get this vector potential factors, V by C factor here, which is what we see as a dipole, anisotropy, and so on. So I can get everything from Galilean transformation. Lorentz transformation is not what is valid. This is what Bondi also mentioned earlier, several decades ago. The universe is not Lorentz invariant. So again, this gravitational potentials, whether you are uniformly moving or stationary, it is the same value everywhere in the universe to a great accuracy. Therefore, the cosmological principle and the principle of relativity, they are intimately related. Cosmological principle is same as a principle of relativity, because one is talking about the uniformity, homogeneity, and isotropy of the gravitational potential, not the distribution of matter. Now, I don't want to, so there is a important slide, but this I don't want to spend time because there is not much time. All I want to say is that the same physics, the metric which I showed there, 1 minus v square by c square, there's a v by c, from which I can derive the fact that the inertia of a gravitational mass m arises from the interaction of matter with the gravity. All that the relativistic form of the inertial mass I can derive. I'm saying it is very rigorous and very complete kind of a calculation. What we call inertia is this combination, gravitational mass multiplied by the gravitational potential of the universe. That's what inertia is. And from which I can derive the Newton's law of motion. That is, I'm saying, from cosmological physics. And this metric calculated in this picture, I can derive Newton's law of motion. So Newton's law of motion is a gravitational law. It is the equivalent of Lenz's law in electrodynamics. Okay. All these facts are detailed in my book. So now all dynamics and motion relativistic effects are determined by the gravity of the matter in the universe, which are detailed in these two books. I invite you to look at it because within a short talk, I cannot explain everything. But I want to say that some very important open problems are completely solved in this approach. The physical basis of principle of relativity, cosmological principle, origin of inertia, inertial forces, physical reason for the equivalence principle, because once you solve the problem of inertia, you get the equivalence principle. The physical reason behind the motional time dilation, of course. The problem, enigma of unipolar induction. From Faraday's time, you don't even see it in textbook discussed because it's embarrassing for special relativity. But okay. The spin statistics connection, the quantum mechanics of spins, that the behavior of fundamental particles, difference between bosons and fermions, is related to cosmic gravity. It's so surprising. It's a beautiful revelation which happened automatically from all this. I didn't force it on the calculation. It came out. Then the microscopic theory of fraction quantum Hall effect and so on. So there are a series of important problems I'm able to handle now. So I conclude with this letter from Galileo to Kepler. Okay, I'm not complaining about standard physicist's attitude towards what I'm doing. I'm also a standard physicist in some sense. I might have responded the same way if somebody else had done this work, I don't know. But let me read this. My dear Kepler, I wish that we might laugh at the stupidity of the human herd. What do we have to say about the principal philosophers of this academy who are filled with the stubbornness of an asp and do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times. Truly, just as the asp stops its ears, so do these philosophers shut their eyes to the light of truth, which is it is old story, but it's the same story which we keep saying. Uh, the previous talk mentioned this. We are the problem. It's a human social problem. The earlier we understand and recognize the unavoidable need for this major paradigm change in fundamental physics, the wiser and less embarrassing it will be for our declared pursuit of a truer description of the physical world. Thank you very much.
That was excellent. Thank you. I cannot think of a better way to conclude the session and also to lead us into the workshop tomorrow where Martin Lopez Corredor will be giving a talk. Patrick will be leading this Future of Cosmology workshop. And so I think that these ideas will really push us into that. And so for now, let's have some questions. Questions.
Yeah, thanks for this. I think one of the most important talks of this conference. I was always trying to stay away from relativity theory as much as possible. So excuse me if I'm going to ask stupid questions. But if I would be an opponent of your theory, of your let's say proofs of refutation of the relativity theory, I would think of saying something like, okay, you assume in many of your proofs that you have that you're working in the stationary frame of the Earth, but it's rotating. So you have to basically do all of these calculations, taking into consideration this rotating frame, and then using the let's say more absolute frames that you need to use for having the real constant light
Yes.
velocity. Did you take that into account in these cases, and
Yes.
how did you do then the calculations?
See, finally, in this formulation, everything is Galilean, so it's very easy to take care of rotation. But going back to history, see, the two people who looked at rotation in the context of a ether theory, one was George Sarnac in France, another was Michelson. Sarnac did this experiment in the laboratory in a rotatable frame and measured the fact that the relative velocity of light in one direction is different from the light going in the other direction, and tried to convince people that there's a problem with special relativity, but people did not listen to it. Even while Einstein's famous visit to Paris in 1922, Sarnac was present in the audience trying to argue with Einstein, but he got so emotional, he spoiled his chance of arguing. Einstein just kept quiet. Everybody kept quiet. That was the end of this debate. Michelson had the same idea in 1904. He published a paper saying that he wants to do this experiment. So he said, okay, well, I couldn't detect the linear motion of the earth through the ether, but I might be able to detect the rotational motion of the earth in the ether. And he had an idea to do this experiment, but it was an expensive experiment to conduct. So he managed to do it only in 1925, which is known famously as the Michelson-Gale experiment. It's published in Astrophysical Journal in 2 papers. This is a remarkable experiment because in 1925, he constructed a large interferometer with a one arm, 1 kilometer in size, like the gravitational wave detectors today. And he measured this rotation of the Earth by just using interferometry and published the paper. In the abstract of the paper, he says the relative velocity of light in one path is different from going in the other path. So there's a history to it already. And in my book, I calculate everything taking into account all this. Yeah.
And so a little follow-up question, is this yeah, let's say disproof of the Michelson-Morley experiment as evidence for the special relativity theory, has this been published in peer-reviewed journals? Because it must.
Right. So you can guess
possible.
what the answer is. No, it's not very bad. See, it depends on what you consider as peer review. For example, this paper is actually from a conference, but it's peer reviewed in the sense within the conference it was peer reviewed. Now you can always say that, oh, this is not a proper peer. I mean, you can always say that. But that's why I say I gave this particular proof, which is a universal peer reviewable proof. Anybody from high school student to an expert relativist can look at this, which is just a logical situation saying that Einstein's hypothesis is internally inconsistent, and try to break that argument. I'm sure nobody will be able to. It's impeccable.
Thanks.
Thank you for a completely fascinating talk. In your opinion, would the statement, is space-time doomed, applicable?
See, one of the book which I showed that Gravity's Time, I analyzed this question of physicality of space and time in great detail. Space is still a bit of a difficult concept for me, but time is something which I understand very well. Where I conclude that in a world in a space where there is no matter, time doesn't make sense. But even Aristotle knew it in some sense. So, yes. So, when you say space-time, if any physicist who want to use space-time as a very essential concept, as a physical object, I think that is that kind of a theory is not the proper theory. Space-time is a derived, emergent thing because there is matter everywhere. Space is something which we use as a complement to matter, and time is a physical process in that matter. So these are ascribing the same physicality of as matter to space and time is very unreasonable. That's all I can say.
Here, here.
So if I understood you correctly, in special relativity, a moving clock ticks slower than a stationary clock, but in your version, it ticks faster. Is that correct?
In one experiment, see, I didn't explain that experiment fully. If I say that, it will be clear to you. I showed this clock coming back, and my statement that that moved clock ran faster than the stationary clock is a true statement. But instead of sending this clock westwards, if I had sent it eastwards, it would have had a time dilation, which is more than what Einstein's theory predicts.
Okay,
So
so by
it's a proof for absolute velocity as a determining factor for time dilation.
all right, so essentially by sending it westward, it was actually traveling slower.
Yes, exactly.
So
Exactly.
that's compatible with special relativity's relative rate, right? I mean, this experiment was done. People took clocks around the
Right.
Earth in both directions and
So
saw
the
it.
point is that special relativity has only relative velocity deciding every physical quantity. That is not it. Is absolute velocity relative to some single absolute frame which determines the time dilation. That's a lesson from this experiment. But that fact was hidden in the published version. In fact, there's a history to it. If you go back to this was done by two people in Naval Observatory in the US. Their notebooks were declassified at some stage. The page says, "This is disturbing," when they first saw this result. Anyway, so that history is
Okay,
not
then
important.
I don't think I need to ask my second question.
Thank you.
In Einstein's traveling twin thought experiment, one twin travels away from the Earth at relativistic speeds, and when they return, they've aged differently. It seemed to me that there's an inconsistency if you modify that experiment so that the twins travel in relativistic speeds in opposite directions or in different directions. And when they return, due to their different frames of reference, each one should have a different expectation of aging. I was wondering if you saw that as a real inconsistency and how that relates to your
Yes,
with the
yes.
clocks.
See, here I didn't want to discuss twin paradox, though in the book I did discuss in great detail for two reasons. One is all textbook descriptions of twin paradox are entirely wrong.
Okay.
Okay. Now, if I just say entirely wrong, people may not take it very seriously.
Mhm.
But however, in 1918, Einstein himself published a paper
Mhm.
on twin paradox. That's the only paper he wrote on twin paradox, in which he makes a statement that special relativity cannot solve this problem.
Oh.
But, however, so it is written in the form of a dialogue. Somebody asked him, "I have been asking you this question for years. You didn't answer." Then he says, "Yes, I didn't answer because I didn't have an answer."
Hmm.
No.
Hmm.
Special relativity cannot solve this problem. I need general relativity, which I have. I have this new theory now. Now I can combine these two and explain this. He doesn't make a calculation in that particular paper. But he says, if you calculate this, you get the correct answer. And okay.
Yeah.
So what I'm saying is the standard explanations given in special relativity textbook deviate from even Einstein's view on this. But even Einstein's view, one can find gaps in that. What I'm saying is, yes, I found inconsistencies. It was a crucial factor to think about all this in my research path in the initial days. Yes.
The solution would seem to be to have a single frame of reference, which you have.
Yes, that
So,
solves everything.
Yeah.
There is also, even in ether relativity, there is no paradox. Even the old Lorentz Poincare theory, there is no paradox. But of course, here it's the absolute frame is same. Only ether is replaced by gravity of the universe. Yeah.
Thank you.
In an absolute reference frame, is there evidence for Earth moving at presumably hundreds of thousands of miles per hour? And what about Dayton-Miller's interferometry experiments?
Yeah. Okay. Now, even this kind of a theory, absolute frame, and as we know from the old ether theory, the principle of relativity is still valid. The reason is that gravitational potentials are generated by all this matter. If you are uniformly moving, the gravitational potentials are different. It's at a different value, but it has the same value everywhere, in every point in the universe. Therefore, we know that in physics, laboratory physics, we cannot detect a constant potential, whatever the value is. We can only detect a spatial gradient of a potential or a time change, time variation of a potential. Okay. So, therefore, if you move uniformly, it's a different potential, but it's the same potential. Therefore, principle of you cannot detect your motion from that. But if you are accelerating, the potential becomes time dependent, and that is Newton's law. So therefore, you get exactly as in electrodynamics. There's a back EMF there. A charged particle accelerating, there is a back EMF. Here, it's a particle with a mass or energy. So it's I'm using a wrong expression, but a back EMF of gravity is what Newton's law of motion. So what I'm saying is, principle of relativity is still valid, but the second postulate that the propagation of light is with the invariant velocity goes wrong when there is absolute frame, because as soon as there is absolute frame, it's a straightforward prediction that propagation of waves are Galilean.
All right, guys, give it up one more time for Dr. Unnikrishnan.